There is a world in our solar system where rain falls as liquid fuel, where rivers of methane cut through frozen plains harder than stone, where vast seas sit beneath an orange sky so thick with haze that sunlight barely touches the ground. A world that has hidden itself for centuries, not because it was too distant to reach, but because it refused to be seen. And buried beneath that atmosphere may be one of the strangest chemical laboratories in the known universe, a place where the first steps toward life may be unfolding in ways no one expected. This world is Titan, and the truth is, Titan may be hiding far more than the surface. It may be hiding an entirely different way for life to begin. That is why tonight matters. Because what you are about to hear is not just the story of a moon orbiting Saturn. It is the story of how one of the most mysterious worlds in our solar system kept its secrets locked away for more than 350 years, and how each new discovery beneath its atmosphere has forced science to rewrite what a moon can be. If you've ever looked up at the night sky and wondered whether the universe still holds places stranger than imagination itself, then this journey was made for you. And if these quiet journeys into the universe help you rest, think, or drift into sleep with wonder, a simple like helps this story reach others searching for the same quiet escape. Now, as the night settle around you, let your thoughts slow and let the universe open its oldest hidden door. Titan was discovered in 1655 by Christian Huygens, a Dutch astronomer who pointed a handmade telescope towards Saturn and noticed a faint moving point of light beside the ringed planet. At the time, it seemed simple enough. Another moon, another orbiting body in the vast machinery of the solar system, but Titan was never simple. Even from the earliest observations, there was something unusual about it. Titan appeared blurred, softer around the edges than other moons. It looked as though it were wrapped in something. At first, astronomers thought this was just an optical limitation, an imperfection of primitive telescopes. But as telescopes improved over centuries, Titan remained hidden behind the same strange blur. Other moons revealed craters, valleys, ridges, scars from ancient impacts. Titan revealed nothing. Just an orange sphere without detail, without shape, without story. That alone made Titan unique. In planetary science, surfaces are history books. The surface of a world records billions of years of impacts, erosion, tectonic movement, volcanic flows. But Titan gave scientists no surface at all. It was a locked world, and locked worlds are dangerous to science because they force imagination into the empty spaces where evidence should be. Everything changed in 1944 when Gerard Kuiper discovered methane in Titan's atmosphere through spectroscopy. This was the first real clue that Titan was unlike any moon ever found. Methane should not survive long under solar radiation. Ultraviolet light tears methane apart molecule by molecule, breaking it into more complex hydrocarbons and eventually destroying it completely. Based on chemical models, Titan's atmospheric methane should disappear in less than 30 million years, a tiny fraction of the solar system's age. But Titan still has methane, a lot of it, which means something beneath the atmosphere must be replacing it, something active, something hidden. That single fact transformed Titan from an ordinary moon into one of the greatest unsolved mysteries in planetary science. Because moons are not supposed to work like this. They are supposed to be geologically dead, airless, frozen, silent. Titan was none of those things. As observations improved in the 20th century, scientists confirmed that Titan's atmosphere was mostly nitrogen, the same dominant gas as Earth's atmosphere. That was extraordinary. Titan remains the only moon in the solar system with a dense nitrogen-rich atmosphere. Its atmospheric pressure at the surface is about 50% higher than Earth's. If you stood there, the weight of the air pressing against your body would be stronger than at sea level on Earth, and yet Titan's gravity is only about 14% of Earth's. By all expectations, such a small world should not have been able to hold on to such a thick atmosphere. But the cold changes everything. Titan's surface temperature averages around minus 179 degrees Celsius. At that temperature, gases move slowly. Escape becomes difficult. The cold traps the atmosphere like a prison, and inside that prison, chemistry becomes strange. Sunlight strikes methane and nitrogen high above Titan, breaking them apart and forcing them into new combinations. Those reactions create hydrocarbons and nitriles, compounds like ethane, acetylene, Tsugi, and hydrogen cyanide. Over time, these compounds bond into larger and more complex organic structures called tholins, reddish-brown molecules that form the thick orange haze surrounding Titan. This haze is not just atmospheric decoration, it is the reason Titan remained hidden for centuries. It scatters and absorbs visible light so effectively that looking at Titan from space is like trying to see the ocean floor through endless smoke, and yet that haze may be the beginning of something even deeper. Because tholins are organic, not biological but chemical cousins to the building blocks of life. Recent laboratory studies and new planetary models suggest that Titan's atmospheric chemistry may resemble conditions on early Earth before life began. In other words, Titan may be preserving a version of chemical history that Earth erased billions of years ago. And if that is true, then beneath Titan's atmosphere may lie not only rivers and seas, but answers to one of humanity's oldest questions. How does life begin? That is the real mystery hidden beneath Titan's haze. Not just what the surface looks like, but what kind of chemistry has been unfolding there for billions of years in silence. Because beneath the orange sky, something has been happening. Something persistent. Something active. Something alien. And before humanity could uncover its rivers, its methane rain, its hidden seas, or its buried oceans of slush and water, we first had to face a frustrating truth. Titan would not reveal itself easily. For more than 3 centuries it stayed silent, a blurred orange sphere orbiting Saturn, holding its secrets behind a wall of atmosphere so perfect at concealment that even our machines could not break through. But eventually we would send something closer, and when we did, the first glimpse beneath Titan's atmosphere would change everything. What if the greatest secret Titan was hiding was not its surface at all, but the atmosphere itself? Before scientists could even begin asking what lay beneath Titan's orange haze, they first had to confront something far stranger. The haze should not have existed in the first place, because by every rule of planetary science, Titan's atmosphere should have disappeared billions of years ago. And yet it remained, thick and heavy, wrapping the moon in a dense chemical veil, unlike anything found on any other moon in the solar system. That was the first real crack in the mystery. Not the land below, but the sky above. And the deeper scientists looked into Titan's atmosphere, the stranger it became. When the first detailed measurements arrived during the 20th century, researchers expected a thin shell of methane clinging to a frozen moon. Instead, they found something astonishing. Titan's atmosphere was massive, dense, layered, dynamic. At the surface, the pressure was roughly 1.5 times that of Earth's sea level atmosphere. Imagine standing on a moon smaller than Earth, with gravity so weak you could leap 7 times higher than here, yet feeling more air pressing down on your shoulders than you would standing beside the ocean on our planet. That contradiction forced a new question. How could Titan hold on to so much atmosphere? Normally, small worlds lose their gases to space. Gravity simply isn't strong enough to keep them. Earth can hold nitrogen and oxygen because it is large and warm enough for atmospheric stability. Our moon cannot. Mars struggles. Even Mercury is nearly airless. Titan, by comparison, should have been far more vulnerable. But temperature changes everything. Titan is unimaginably cold, averaging around minus 179 degrees Celsius. At that temperature, gas molecules move far slower, carrying less energy, making escape into space far less likely. The cold acts like a lock, trapping the atmosphere close to the surface. It is one of the great inversions of Titan. What seems like weakness, low gravity, becomes strength because of extreme cold. But the composition of that atmosphere was even more surprising than its density. Roughly 95% nitrogen. Nearly the same atmospheric foundation as Earth. This remains one of Titan's strangest traits. Across the solar system, no other moon has anything like it. Nitrogen atmospheres require long-term stability and chemical cycling. They imply a history of internal activity, outgassing and atmospheric evolution. Titan was not a simple frozen object. It was behaving like a planet. And then there was the methane. Methane made up only a small percentage of Titan's atmosphere, but it controlled everything. Because methane on Titan behaves the way water behaves on Earth. It evaporates, condenses, forms clouds, falls as rain, flows across the surface, collects into lakes and seas. This methane cycle creates weather. Weather creates erosion, and erosion reshapes the landscape. In effect, Titan has its own version of a hydrological cycle, except the liquid involved is natural gas. This realization shattered old assumptions. Before Titan, Earth was the only known world with stable liquid cycles on its surface. Titan became the second. But methane comes with a problem. Sunlight destroys it. Every ultraviolet photon from the sun breaks methane apart, splitting carbon from hydrogen and triggering chains of chemical reactions high in Titan's atmosphere. Over time, those reactions convert methane into heavier hydrocarbons and nitriles, ethane, acetylene, hydrogen cyanide, benzene. These compounds combine into larger, stranger molecules, sticky reddish-brown organic substances called tholins. Tholins are among the most important clues in Titan's story. They are not life, but they are chemistry moving in the direction of life, complex carbon structures, formed naturally in an atmosphere, raining down over geological time like chemical snow. Every day on Titan, the sky manufactures organics. Every day, those organics drift downward to the surface, over millions of years that creates vast deposits of prebiotic material. Scientists now believe Titan's surface may be coated in layers of organic sediment, hundreds of meters thick in some places, a planet-sized chemistry experiment running for billions of years. And this creates the deeper frustration. If sunlight is destroying Titan's methane constantly, then where is the new methane coming from? It has to come from somewhere. The atmosphere cannot sustain itself forever. Current estimates suggest Titan's methane reservoir should be exhausted in less than 50 million years unless it is replenished. But Titan is over 4 billion years old. That means something inside Titan is feeding the sky. Some scientists believe methane may be trapped in clathrate ice beneath the surface, frozen into crystal structures that slowly release gas over time. Others propose cryovolcanism, icy volcanoes erupting methane and water ammonia mixtures from deep underground. More recent models suggest methane may seep upward through fractures from Titan's deep interior, escaping from buried reservoirs left over from the moon's formation. No one knows for certain, and that uncertainty matters, because wherever the methane comes from, it connects the atmosphere to the interior. The sky and the hidden layers below are part of the same system, a breathing system, a cycling system, a world where surface, atmosphere, and deep internal chemistry are all connected, and above all of this hangs the haze. Thick, orange, endless haze, not clouds, not fog, but suspended organic particles filling the atmosphere from hundreds of kilometers above the surface all the way down into the lower layers. This haze is why Titan remained hidden for centuries. It absorbs visible light so efficiently that sunlight cannot penetrate clearly, and reflected light cannot escape cleanly. To human eyes, Titan is a mask, but masks are powerful because they force patience, and patience in science often leads to revelation. For centuries, Titan's atmosphere was a wall, a barrier no telescope could cross. But eventually, humanity built machines that could do more than look. Machines that could touch. Machines that could descend. And when one of them finally entered Titan's atmosphere, for the first time in history, humanity would taste the alien air from inside the veil itself, and what it found falling through that orange sky would reveal the first true shape of the hidden world below. By the time humanity entered the space age, Titan had become more than a moon. It had become a challenge. For centuries, telescopes had failed to see through its haze, but spacecraft promised something different. Spacecraft could get closer. Close enough, scientists believed, to finally tear away the orange curtain and expose whatever Titan had hidden for so long. That hope first arrived in 1979 when Pioneer 11 crossed the Saturnian system, delivering humanity's first direct images of Titan. But the images were disappointing. Titan appeared smooth, featureless, an orange sphere without detail. It was as if the moon had erased itself. Still, Pioneer's cameras were primitive by later standards, and scientists remained confident that the real breakthrough would come 1 year later with Voyager 1. Voyager 1 was one of the most ambitious scientific machines ever built, carrying cameras and instruments far beyond anything Pioneer possessed. Mission planners made a remarkable decision. They changed Voyager's trajectory specifically to encounter Titan. This was no small sacrifice. By targeting Titan closely, Voyager gave up its chance to continue toward Uranus and Neptune. 2 entire planets were traded for 1 moon. That decision reveals how important Titan had become. Scientists believed Titan might hold answers about atmospheric evolution, chemistry, and perhaps the conditions of the early Earth. In November 1980, Voyager 1 passed within about 6,500 kilometers of Titan's cloud tops. It was supposed to be the moment of truth. But when the images came back, the truth was infuriating. Titan still showed nothing. Not a crater, not a mountain, not a river valley. Nothing but orange haze, brighter and sharper than Pioneer's images, but equally empty. Imagine sacrificing 2 planets for a close look at 1 moon, only to find the same blank mask. Scientists tried everything: contrast enhancement, wavelength filtering, image stacking. Nothing worked. The haze defeated every optical technique. Titan had won again. But Voyager's failure to see the surface became a success in another way. Because while the cameras failed, the instruments succeeded. Voyager measured the temperature profile of Titan's atmosphere, confirming its immense thickness and complexity. It mapped layers of hydrocarbons and nitrogen, detected high-altitude photochemical reactions, and revealed a strange detached haze layer far above the main atmosphere. This detached haze was especially mysterious. It floated like a second atmosphere above the first, shifting with Titan's seasons. Later observations would show that these haze layers move and evolve over decades, driven by atmospheric circulation patterns unlike anything on Earth. Voyager also revealed the scale of Titan's chemical machine. Methane in the upper atmosphere was constantly being destroyed by sunlight and converted into heavier hydrocarbons. Ethane was accumulating. Hydrogen cyanide was forming. Benzene molecules appeared. Titan's atmosphere was manufacturing complexity. That was a profound realization. because chemistry on Titan was not static. It was alive with reaction, and those reactions had consequences. Everything produced in the sky had to go somewhere. Gravity pulled those molecules downward. Over time, they rained onto the hidden surface below. Scientists began asking an uncomfortable question. If Titan's sky has been producing organic material for billions of years, how much has accumulated on the ground? Some estimates suggested hundreds of meters of hydrocarbon sediment. Others suggested deep oceans of liquid ethane. The uncertainty was enormous because no one could see the surface. The atmosphere was forcing science into speculation. Some believed Titan was covered by a global hydrocarbon ocean. Others argued for solid organic sludge. A few proposed mixed landscapes with rivers and lakes. But without images, all models remained guesses. Yes, Titan became a scientific mirror. Researchers saw in it whatever their theories allowed, and the longer Titan remained hidden, the stranger those theories became. Yet Voyager left behind something more important than answers. It left behind urgency. Titan was now officially one of the highest priorities in planetary science. A moon with weather, a moon with chemistry, a moon that might preserve ancient organic processes similar to those that preceded life on Earth. But to understand Titan, looking from above would never be enough. Humanity would have to go through the atmosphere itself, through the haze, through the orange wall. And that meant building something no mission had ever attempted before. A machine designed not to orbit Titan, but to fall into it, to uncover Titan's secret. Scientists realized they needed to stop looking at it like astronomers and start approaching it like explorers. Telescopes had failed, flybys had failed, cameras had failed. The only way to know what Titan was hiding was to enter its atmosphere directly, descend through the haze, and survive whatever waited below. That was the beginning of one of the boldest engineering decisions in the history of space exploration. The mission that became Cassini-Huygens was not built simply to study Saturn. It was built, in part, to solve Titan. The Cassini orbiter would circle Saturn and repeatedly pass Titan, using radar and infrared instruments to penetrate the haze. But the real gamble was Huygens, a small probe designed to detach from Cassini and fall into Titan's atmosphere like a human-made meteor. Named after Christian Huygens, he is the man who first discovered Titan. The probe carried humanity's first attempt to land on a world no one had ever seen. This was a dangerous idea. Titan's atmosphere was only partially understood. Scientists knew it was thick, but not exactly how thick. They knew methane existed, but not how clouds behaved. They knew the surface might be solid, liquid, or something in between. Huygens had to survive all possibilities. If Titan had an ocean, it had to float. If it had mud, it had to land without sinking. If it had rock, it had to withstand impact. Every scenario required a different engineering solution. The result was a machine built for uncertainty itself. Huygens was about 2.7 meters wide, protected by a thick heat shield to survive atmospheric entry. Inside were 6 scientific instrument systems: cameras, spectrometers, atmospheric sensors, wind detectors, and a surface impact analyzer. Each instrument had one purpose: answer the questions Titan had denied for centuries. What is in the atmosphere? How thick is the haze? What does the surface look like? What is it made of? Is it wet? Dry? Solid? Alive with chemistry? Cassini-Huygens launched in 1997 on a 7-year journey to Saturn, using gravity assists from Venus, Earth, and Jupiter to build enough speed to reach the outer solar system. The spacecraft itself was enormous, nearly 6 tons fully fueled, carrying both the orbiter and the lander. It entered Saturn orbit in 2004. becoming the first spacecraft ever to orbit the ringed planet. For months, Cassini studied Saturn and Titan from orbit, refining atmospheric models and testing communications with Huygens. During these early flybys, as Cassini's radar did something revolutionary, it penetrated the haze. For the first time, blurry radar maps began sketching Titan's hidden surface. The maps were crude, but they showed variation: bright regions, dark plains, rough textures, smooth patches, patterns resembling coastlines. Titan was not uniform. Already the old models were collapsing. This was not a global ocean, not a single endless sludge field. It was a world with geography. But radar alone could not tell the whole story. The surface still needed to be touched. On Christmas Day 2004, Cassini released Huygens. No engines fired, no dramatic thrust. Springs gently pushed the probe away at walking speed. It drifted silently for 20 days toward Titan, alone in deep space, aimed by calculations made years before. No corrections, no steering. He is just falling toward an unknown world. On January 14th, 2005, Huygens struck Titan's upper atmosphere at nearly 6 kilometers per second. The heat shield glowed white-hot as friction ripped energy away from the probe. Then the parachutes deployed. First the drogue chute, then the main parachute. And for the first time in human history, instruments began tasting the air inside Titan's atmosphere. Nitrogen, methane, hydrocarbons, wind speeds, temperature gradients, pressure changes. The descent had begun, but for the first minutes the camera saw nothing, only orange fog, endless haze. The same haze that had defeated telescopes for centuries was now surrounding the probe itself. Titan was still resisting. But below that haze something was waiting. And as Huygens fell deeper, the fog began to thin. Shapes began to emerge. Lines, shadows, patterns. For the first time in history, Titan's hidden world was beginning to appear, and what appeared below looked disturbingly familiar. Like rivers, like coastlines, like Earth, only colder, stranger, and impossible. The first shapes Huygens saw beneath Titan's haze were impossible to ignore. At first, they were only shadows, faint lines cutting across brighter terrain. But as the probe descended lower, those lines sharpened into something unmistakable: river channels. Long branching networks stretched across the surface, splitting and merging exactly the way rivers do on Earth. For centuries, Titan had hidden itself behind orange fog, and now the first clear evidence revealed a landscape shaped by flowing liquid. But this was not water. On Titan, water is frozen solid, harder than granite under temperatures near -179 degrees Celsius. The rivers were methane, liquid natural gas flowing over bedrock made of ice. It was one of the strangest geological reversals ever seen. On Earth, rock is solid and water is liquid. On Titan, ice is the rock and hydrocarbons are the liquid. That inversion changed everything. The channels Huygens photographed were not random cracks. They had the signatures of erosion. Tributaries fed larger channels. Valleys widened downhill. Dark plains collected the runoff below. It looked like a drainage basin, a system shaped by repeated rainfall and flowing rivers over long periods of time. This was not ancient geology frozen in place. This was active climate. Titan had weather. That realization transformed Titan overnight. Until then, Earth had been the only known world with a stable cycle of liquid moving between sky and surface. But Titan had its own version. Methane evaporated from the ground, rose into the atmosphere, condensed into clouds, and fell as rain. A complete weather cycle. Different liquid, same process. It was a second hydrological system in the solar system. But stranger still was where Huygens landed. The probe struck a flat dark plain scattered with rounded pebbles of water ice. Rounded, smooth, worn down. To geologists, that shape means transport by flowing liquid. Sharp rocks become round when rivers carry them, tumbling them against each other over time. Titan's pebbles told the same story. Rivers had once flowed here, maybe recently. Instruments detected a spike in methane right after landing, likely caused by liquid methane evaporating from damp ground disturbed by impact. Huygens may have landed in a dry riverbed, a place wet not long before. For 72 minutes after landing, Huygens transmitted data back to Earth. Images, chemistry, surface texture, temperature, wind. In just over an hour, it changed planetary science forever. Titan was not dead, not silent, not frozen in geological time. It was active, evolving, weathered. But Huygens had landed near Titan's equator, in a relatively dry region. Scientists quickly realized the real story might be elsewhere, because Cassini's radar, still orbiting above, was about to reveal something even bigger than rivers. Not channels, not streams, entire seas. If Titan's rivers were surprising, its seas were almost unbelievable. When Cassini turned its radar toward Titan's north pole, scientists expected rough plains or icy terrain. Instead, the radar returned something strange. Blackness. Perfect black shapes stretching across the surface. In radar images, black means smooth. Extremely smooth. On Earth, only liquid produces that kind of reflection. At first, scientists hesitated. Could it be instrument error? But pass after pass confirmed the same thing. Titan had lakes, and not just lakes, seas. Massive bodies of standing liquid spread across its polar regions. The largest, Kraken Mare, stretches over 1,000 kilometers across, larger than many seas on Earth. Beside it lay Ligeia Mare and Punga Mare, vast hydrocarbon basins filled not with water but methane and ethane. Titan became the only world besides Earth known to have stable liquid seas on its surface. This was a turning point. Because seas mean coastlines, waves, evaporation, rainfall, climate, a complete planetary system operating in liquid form. Cassini confirmed the seas were real through multiple methods. Radar reflections showed mirror-like glints from smooth liquid surfaces. Infrared instruments caught sunlight reflecting off the lakes like sunlight on water. Some radar pulses even penetrated the liquid and bounced off the lake floor, measuring depths of over 100 meters. Titan's seas were not shallow puddles. They were deep basins carved into the moon's crust, and they were dynamic. Shorelines shifted. Liquid levels rose and fell. Some lakes showed ring-like deposits along their edges like bathtub rings, suggesting evaporation over time. Titan's climate was active, seasonal, changing. But one mystery stood out immediately. Why were almost all the large seas in the north? Titan's southern hemisphere was comparatively dry. Scientists eventually linked this imbalance to Titan's seasons. Saturn's orbit around the Sun is slightly elliptical, causing uneven seasonal heating. Titan's northern summers are longer and cooler, allowing methane to remain stable. Southern summers are shorter but warmer, driving stronger evaporation. Over thousands of years, the liquid migrated north. Climate was shaping geography. Cassini also detected clouds forming over Titan's poles and equator. Some storms were massive, spanning hundreds of kilometers. In 2009, scientists observed darkening on Titan's surface after a major storm, thus evidence of fresh methane rain soaking the ground. They were watching weather happen on another world. Imagine standing on Titan during a storm, huge methane droplets falling slowly through thick orange air, drifting like glass beads in twilight, rivers filling, valleys flooding. liquid fuel running across ice harder than a rock. It sounds impossible. But it is real, and Titan's seas introduced a new possibility. If methane could collect, flow, and cycle on the surface, then chemistry could concentrate there. Complex organics from the atmosphere could dissolve in the lakes, react and evolve into new structures. Some of the most recent laboratory studies suggest that under Titan-like conditions, cell-like membranes could form naturally inside hydrocarbon liquids, not life, but the architecture of life. And if that could happen on the surface, what might be happening deeper below? Because beneath Titan's seas and beneath its frozen crust, something even stranger may be waiting. Not methane this time. Water. Warm liquid water hidden in darkness, and that discovery would change Titan once again. Titan's seas did more than prove that liquid could exist on another world. They revealed something far more unsettling. Titan was running chemistry on a planetary scale. Every drop of methane rain, every river channel, every dark sea at the poles was part of a chemical machine that had been operating for billions of years. And unlike Earth, Titan preserved that chemistry in cold, slow motion, almost like a frozen memory of the early solar system. High above Titan's surface, sunlight strikes methane and nitrogen, breaking molecules apart and forcing them into new combinations. Carbon fragments collide, hydrogen escapes, nitrogen bonds with carbon, forming compounds like hydrogen cyanide, acetylene, and ethane. These are not random chemicals. On Earth, molecules like these are deeply connected to prebiotic chemistry, the chemistry that existed before life. Over time, these molecules grow more complex, linking into larger organic chains that drift downward like orange dust. Scientists call them tholins, and Titan produces them constantly. Every day, more organic material falls from the sky. Imagine chemical snow coating the landscape for millions of years. Rivers wash it into valleys, lakes dissolve it, winds move it into dunes. The entire moon recycles carbon through sky, land, and sea. It is a world-sized chemistry experiment. That matters because chemistry needs concentration. On Earth, life began when molecules stayed together long enough to react repeatedly. In oceans, pools, and coastlines, chemistry became more organized. Titan may offer a similar system, but with methane replacing water. Recent laboratory experiments have shown that certain organic molecules under Titan-like temperatures can form membrane-like structures in liquid hydrocarbons, tiny compartments, primitive boundaries. The kind of structures life on Earth depends on, scientists call them vesicles. These structures are not alive, but they represent one of the earliest possible steps toward life, separation between inside and outside. A chemical self. On Earth, water drives this process. On Titan, methane may do it differently. That possibility changes astrobiology. It suggests lifelike chemistry may not require Earth-like conditions, but Titan's surface is brutally cold, too cold for water-based biology as we know it. Which raises the deeper question, if the surface is chemically rich but frozen solid, could warmth exist somewhere below? Because beneath Titan's rivers and seas lies a shell of water ice hundreds of kilometers thick, and under that shell something may still be moving. For years, scientists believed Titan hid a global ocean beneath its crust. The evidence came from gravity. Every time Cassini flew past Titan, it measured tiny changes in the moon's gravitational pull. Those changes revealed how Titan flexed under Saturn's tidal forces, and Titan flexed too much to be completely solid. The simplest explanation was liquid water beneath the ice, a hidden ocean. Yes, that idea was revolutionary. Titan would not just have methane seas on the surface, but a second ocean beneath, made of water. Two separate liquid worlds stacked on top of each other. For astrobiology, that was extraordinary. Water is the universal solvent of life on Earth. If Titan had a buried ocean touching rock below, chemical reactions could happen there, powered by heat from the interior. But in late 2025, new analysis changed the picture. Scientists reprocessed Cassini's old Doppler data with improved techniques and found something unexpected. Titan's interior might not be a smooth ocean at all. Instead, it may be slush, a vast layer of partially melted ice, filled with pockets and channels of liquid water trapped between crystals. Not an open sea, but a frozen labyrinth. That difference matters. An ocean circulates freely. As slush moves slowly, grinding and flexing under pressure, the friction creates heat. That heat could form warm liquid pockets near Titan's rocky core. Some models suggest these pockets may reach temperatures near room temperature, warm enough for active chemistry. Imagine it. Beneath hundreds of kilometers of frozen crust, hidden in darkness, isolated pockets of warm water slowly moving through icy slush. Organic molecules from the surface could sink downward through fractures. Minerals from the rocky core could dissolve upward into the water. For brief geological moments, chemistry from two worlds might meet. Surface organics, subsurface water. This makes Titan stranger than Europa or Enceladus. Those moons may have cleaner oceans. Titan may have messier chemistry, more isolated, more complex, perhaps even more experimental. And if life needs diversity of conditions, Titan may offer exactly that. Not one ocean, but thousands of tiny chemical laboratories buried in ice. But the question remains, can any of that chemistry sustain life? Or is Titan simply the universe's most beautiful unfinished experiment? The answer may depend on what Dragonfly finds when it arrives, because humanity's next journey to Titan will not float or orbit, it will fly. For all that Cassini and Huygens revealed, Titan remains mostly untouched. We have seen rivers, seas, dunes, storms, and the outline of a hidden interior, but we have never truly explored its surface. We have never picked up its organic sands, tested its chemistry directly, or searched for the molecules that might sit on the edge between chemistry and biology. That is why the next mission to Titan may become one of the most important in modern planetary science. Its name is Dragonfly. Unlike every rover sent to Mars, Dragonfly will not crawl, it will fly. Titan makes flight strangely easy. Its atmosphere is 4 times denser than Earth's, while its gravity is only about 1/7 as strong. That means lifting off Titan's surface requires far less energy than lifting off Earth. A machine the size of a car can move through Titan's air with remarkable efficiency, hopping from site to site across vast distances. Dragonfly is designed as an 8-rotor flying laboratory, powered by a nuclear battery so it can survive Titan's weak sunlight and freezing cold. When it arrives in the 2030s, it will land near Selk Crater, an ancient impact basin where scientists believe liquid water may once have existed temporarily after the collision. That detail matters. When an asteroid strikes an icy world, the impact heat melts enormous volumes of ice. For a brief period, sometimes thousands of years, liquid water can exist on the surface before freezing again. If Titan's surface organics mixed with that water, chemistry may have advanced far beyond what we can imagine. Dragonfly's mission is simple in concept, but enormous in importance. Find out how far Titan's chemistry has progressed. It will sample the ground, analyze organic molecules, measure atmospheric conditions, and search for compounds linked to prebiotic chemistry, amino acids, complex hydrocarbons, nitrogen-rich organics. Molecules that may reveal whether Titan's chemistry is climbing toward life or stalling just below it. But Dragonfly will also do something else. It will test Titan as a system, how surface chemistry connects to atmospheric chemistry, how weather shapes organics, how dunes move, how methane alters the landscape. For the first time, Titan will not be observed from a distance, it will be explored directly. And that matters, because Titan may be telling us something much larger than its own story. It may be showing us that the ingredients of life are not rare, that chemistry itself wants to organise given enough time, enough energy and the right environment. But Titan also forces a harder question. If all these ingredients exist, why has life not appeared? Or has it? When most people imagine life, they imagine water, oxygen, sunlight, warmth. Titan offers almost none of that. Its surface is frozen beyond anything Earth naturally experiences. Oxygen is absent. Water is locked into stone-hard ice. By traditional standards, Titan should be lifeless. And yet Titan keeps violating expectations. It has organic chemistry everywhere. Liquid cycles, energy gradients, atmospheric reactions, surface reservoirs, internal heat. These are not small details. They are the ingredients that life needs, just arranged differently. That has led some scientists to ask a dangerous question. What if Titan hosts a kind of life we would not recognize? Not water-based life, methane-based life. The idea sounds extreme, but chemistry allows strange possibilities. On Earth, cell membranes form because water forces certain molecules into organized boundaries, but on Titan, methane could drive similar organization through different molecules. Laboratory simulations have shown that membrane-like structures could theoretically form in liquid methane under Titan conditions. If stable enough, such structures could separate internal chemistry from the outside world, one of the basic requirements of living systems. But metabolism is harder. Life needs energy. On Earth, organisms harvest energy by breaking chemical bonds or using sunlight. Titan's surface offers little sunlight, but chemistry itself may provide energy gradients. Hydrogen from the atmosphere, acetylene on the surface, methane as solvent. Some models suggest that hypothetical methane-based microbes could exploit these reactions, slowly, in extreme cold, using entirely different biochemical rules. So far, there is no evidence that this exists. No confirmed biosignature, no strange patterns in methane consumption, no direct detection of metabolism, but the idea remains scientifically possible. More likely, if life exists on Titan, it may be below the surface, inside those warm liquid water pockets trapped in slushy ice. There, water-based chemistry could happen as it does on Earth, protected from the brutal cold above. Organic molecules from the surface could sink downward. Minerals from the rocky core could rise upward. In those hidden chambers, chemistry might have had millions of years to experiment. But even if Titan is lifeless, its value does not disappear. In some ways, that would be even more useful, because Titan may show us the exact boundary where chemistry almost becomes biology, but does not cross it. That boundary is one of the greatest mysteries in science. Where does life begin? At what moment does chemistry become something more? Titan may hold that answer, not because it is alive, but because it may be the closest natural model of life's beginning that still exists, hidden beneath orange haze, waiting in cold silence. And the deeper we look, the more Titan seems less like a moon, and more like a world that rewrote the rules long before we ever arrived. If Titan's rivers and seas feel strangely familiar, its deserts feel even stranger. Because stretching across Titan's equator are vast dune fields, endless dark ridges running for hundreds of kilometers, shaped by winds moving through the thick orange air. At first glance, they resemble the great deserts of Earth, like the Sahara or the Namib. But Titan's dunes are made of something no desert on Earth has ever known. Not quartz, not rock. Organic particles, tiny carbon-rich grains born in the atmosphere itself. High above Titan, sunlight breaks methane apart, creating complex hydrocarbons that slowly fall to the ground like chemical dust. Over millions of years, those particles gather on the surface, dry under rare sunlight, and are lifted by Titan's winds into long parallel dunes. Imagine standing there, black sands beneath your feet, made from molecules that were once floating in the sky, a desert built by atmospheric chemistry. Titan's dunes cover nearly 20% of the Moon's surface. Some rise more than 100 meters high. Their shape tells scientists something important. Titan's winds are stronger and more organized than expected. For years, models suggested Titan's thick atmosphere would suppress movement, but the dunes proved otherwise. Seasonal storms and shifting air currents move material across the equator, slowly reshaping the landscape. These dunes are more than scenery, they are storage systems for chemistry. Every grain holds organic material, preserving carbon compounds over geological time. If methane rain or impact heat ever mixed with these dunes, the chemical possibilities multiply. Water ice, organics, energy, and time, the ingredients align again. Titan's deserts are not empty. They are archives of chemistry spread across a frozen world like pages in a book waiting to be read. And hidden between those dunes are places where something even more violent may have happened. Because on Titan, impacts do not just make craters. They may briefly create lakes of liquid water. Impact craters are scars of violence. Across the solar system, they record ancient collisions, moments when asteroids struck worlds and reshaped their surfaces forever. But on Titan, craters may hold something far more important than damage. They may hold the memory of liquid water. When a large asteroid hits Titan, the energy released is enormous. The Moon's crust, made mostly of water ice, melts instantly under the heat. For a short time, what was once solid ice becomes liquid water, not methane, water, warm, reactive, and temporary. This creates something extraordinary, an oasis of liquid water on one of the coldest worlds in the solar system. Scientists believe these temporary melt pools could last hundreds or even thousands of years before freezing again. That may sound brief, but in chemistry it is enough. Organic molecules coating Titan's surface could dissolve into those waters, react, combine, and form more complex structures. It is one of the most promising natural experiments in prebiotic chemistry anywhere in the solar system. Selk Crater, the future landing site for Dragonfly, is one of these locations. Roughly 80 kilometers wide, it was formed by a major impact long ago. Scientists suspect that after the collision, liquid water pooled across the crater floor, mixing with Titan's organic-rich surface material. If complex chemistry happened there, traces may still remain frozen in the sediments. Dragonfly will search for them. Amino acid precursors, nitrogen-rich compounds, patterns of chemical organization that hint at increasing complexity. Titan's craters are like time capsules. They preserve moments when impossible conditions briefly became possible. Warmth in a frozen world, water on a moon of methane. Here, opportunity for chemistry to leap forward. This is what makes Titan so compelling. It keeps creating temporary bridges between environments that normally stay separated. The sky creates organics, the surface stores them, impacts melt ice into water. The interior may contain warm, slushy pockets. Again and again, Titan creates places where chemistry can experiment. Not continuously, but often enough. And in the universe, sometimes often enough, is all life needs. But there is one final layer beneath all of this. A deeper mystery than the rivers, the dunes, or even the hidden water pockets. A mystery about how Titan itself was born. Because some scientists now believe Titan may not have formed the way we once thought at all. For centuries, Titan seemed ancient, stable, almost timeless. a moon that had quietly orbited Saturn since the birth of the solar system. But recent models suggest something far less peaceful. Titan may not have formed gently at all. It may be the product of a colossal collision between two ancient moons, a violent merger powerful enough to melt ice, rearrange rock, and completely reshape its internal structure. This idea emerged from orbital simulations studying Saturn's crowded moon system. Over billions of years, gravitational interactions can destabilize orbits, causing moons to migrate, resonate, and sometimes collide. In some models, Titan's current orbit and its strange relationship with Hyperion make more sense if Titan absorbed another moon in the distant past. If true, this changes everything. A collision of that scale would release unimaginable heat. Much of Titan's interior could have melted, resetting its thermal history and redistributing its layers of rock and ice. The event could explain why Titan has relatively few impact craters compared to what scientists expect for such an old world. Its surface may have been resurfaced, either directly by the collision or by the geological activity triggered afterward. A violent birth would also help explain Titan's unusual chemistry. Internal heat from a merger could have trapped methane deep inside the crust, slowly leaking upward over millions of years and feeding the atmosphere we see today. It could also explain the slushy interior, where partially melted ice still shifts under Saturn's tides. In a way, Titan may still be carrying the heat of an ancient wound. Imagine two icy moons colliding in the darkness around Saturn, or mountains of ice vaporized instantly, rock shattered and mixed. Shockwaves travelled through both bodies, fusing them into one larger world. That world cooled, hardened, and eventually became Titan. But the evidence of that violence may still remain buried inside. If Titan was born this way, then its story is not one of quiet formation, but survival. A world forged in impact, wrapped in atmosphere and shaped by billions of years of chemical evolution. It would mean Titan's mystery began not with the haze, but with catastrophe itself. And if that is true, then every layer of Titan, from the atmosphere to the deepest water pockets, may be a consequence of that forgotten collision. But Titan's greatest mystery may not be its origin. It may be what it tells us about worlds beyond our solar system. Titan forces an uncomfortable realization. For decades, when scientists searched for habitable worlds, they focused on Earth-like planets, rocky surfaces, liquid water, warm sunlight. The habitable zone around stars became the center of the search for life. Titan breaks that idea apart. Titan is far outside the Sun's habitable zone. Its surface is nearly 200 degrees below freezing. By classical standards, it should be irrelevant to biology. And yet it may be one of the most chemically active worlds we know. It has weather, seasons, liquid cycles, organic chemistry, possible subsurface water, energy from tidal forces, in other words, many of the conditions needed for complex chemistry, just arranged differently. Titan teaches us that habitability may not be limited to warm planets with surface oceans. It may emerge in hidden places, inside ice, beneath atmospheres, around giant planets far from starlight. That changes the search for life across the galaxy. Because gas giants are common, and where there are gas giants there may be moons, thousands, millions, perhaps billions of them. If even a small fraction are Titan-like, the universe may be filled with chemically rich worlds we have barely imagined. Cold worlds with hydrocarbon rain, thick atmospheres, buried water, strange chemistry moving toward complexity and silence. Titan is our first proof that such a world can exist, not in theory, not in simulation, here, in our own solar system. That is what makes Titan so unsettling. If we had discovered Titan orbiting a distant star, we would call it one of the most extraordinary exoplanets ever found. We would debate its chemistry, speculate about its oceans, dream about sending probes. But Titan is near distant. It has been here the whole time, orbiting Saturn while humanity looked elsewhere. That is the deeper lesson. The universe hides its strangest worlds not only in distant galaxies, but sometimes right beside us, hidden by atmosphere, hidden by assumption. Titan reminds us that alien does not mean far away. Sometimes alien is simply something we fail to understand, and Titan may be the greatest example of that in the solar system, a world that looked simple from a distance, but turned out to contain seas, storms, chemistry, and perhaps the earliest ingredients of life. A world that forces us to rethink what life needs, where chemistry can evolve, and how strange the path from matter to biology might truly be. And still, after everything we have learned, Titan remains mostly unexplored. The orange haze is thinner now, but the mystery beneath it is far from over. Because the next time humanity touches Titan, it will not simply observe, it will search, and what it finds may change the story once again. Titan should not have weather, not by the standards we once used to define climate. It is too cold, too far from the sun, too dimly lit to sustain the kind of active atmospheric cycles we associate with living planets. And yet Titan has weather, not frozen and static, but moving, changing, evolving with seasons that stretch across decades. It has clouds that gather and disappear, rain that falls from the sky, storms that darken the land, winds strong enough to shape deserts. In many ways, Titan behaves more like Earth than Mars does. But on Titan, the weather is built from methane. That changes everything. When sunlight reaches Titan's surface, weak as it is, it warms the methane just enough for some of it to evaporate. It rises into the atmosphere, cools, condenses into clouds, and eventually falls back as rain. The process mirrors Earth's water cycle almost perfectly. But because Titan is so cold and its gravity is so weak, the behavior of rain is radically different. Methane raindrops can grow much larger than water drops on Earth. Some models suggest they can reach the size of small marbles before falling, and because Titan's air is so dense they fall slowly, drifting down through orange haze like glass beads suspended in slow motion. When they hit the surface, they feed rivers, flood channels, and refill lakes. Some storms are rare, separated by years or even decades, but when they come violently. Cassini observed darkening on Titan's equatorial surface after major storms, clear evidence of rainfall soaking the ground. Entire regions changed brightness, then slowly dried over time as methane evaporated back into the atmosphere. A complete climate system, a breathing cycle of sky and land. But Titan's weather has another consequence. It moves chemistry. Every storm washes organic material from the atmosphere into the rivers and seas. Every flood redistributes carbon-rich sediments across the moon. Every evaporation cycle leaves behind heavier hydrocarbons. In other words, weather is not just shaping Titan's landscape, it is organizing Titan's chemistry. And chemistry, given enough organization, begins to move toward complexity. Titan's weather may be doing more than sculpting valleys. It may be building the conditions for something larger. Among Titan's many strange places, none are more mysterious than Kraken Mare. It is the largest sea on Titan, stretching over 1,000 kilometers across the moon's northern hemisphere. A sea of methane and ethane, dark as ink, colder than anything on Earth, and hidden beneath the haze for billions of years. Cassini's radar first revealed Kraken Mare as a vast black basin, smooth enough to absorb almost all returning signals. That smoothness meant liquid. But the real surprise was its coastline. Irregular edges, deep bays, long channels, inlets and peninsulas shaped by erosion. It looked like a coastline on Earth. That was shocking because coastlines require movement, waves, currents, changing levels. Titan's seas were not frozen pools, they were active bodies of liquid. More recent models suggest winds moving across Kraken Mare generate waves, small by Earth standards, but enough to reshape shorelines over time. Imagine standing at Titan's coast, a black sea stretching into orange darkness, methane waves lapping against frozen banks of water ice and organic sediment. The liquid would be colder than anything you can imagine, but it would move like water, flowing, shifting, alive with physics. Cassini also detected changes in the levels of some smaller lakes near Kraken Mare, suggesting liquid moves between connected basins, perhaps through underground channels or seasonal overflow. Titan's hydrology is not simple, it is connected, dynamic, a living system of liquid movement across the moon. But Kraken Mare may hold something even more important than climate. It may be one of the best places for chemical concentration. Organic compounds raining from the atmosphere dissolve into the sea, collecting and interacting over time. Unlike on land, where particles remain scattered, liquids bring molecules together, and concentration is one of the first requirements for complex chemistry. Some scientists believe Kraken Mare may be one of Titan's greatest chemical laboratories, where organic molecules gather, collide, and evolve into larger structures. Not life, perhaps, but the road toward it. Future missions may one day send a floating probe or even a submarine into Kraken Mare, diving beneath the hydrocarbon surface to explore its chemistry directly. Until then, Kraken remains one of the greatest unexplored seas in the solar system. Silent, dark, hidden beneath haze, waiting. And beneath that sea, beneath the crust below it, another hidden world may still be moving in darkness. Beneath Titan's frozen surface lies the strangest possibility of all. Not methane, not ethane, but water. Warm liquid water trapped deep below the ice, hidden in darkness where sunlight has never reached. For years, scientists imagined Titan's interior as a single global ocean, a vast hidden sea sealed beneath hundreds of kilometers of ice. But newer models suggest something even stranger. Not one ocean, but countless pockets of liquid trapped inside a slushy layer, scattered like underground lakes inside frozen stone. These pockets may form because of tidal heating. Saturn's gravity constantly pulls on Titan, stretching and compressing it as the moon orbits. That motion creates friction inside Titan's interior. Friction creates heat, and heat melts ice. Then slowly, over millions of years, pockets of water emerge inside the slush. Some models suggest these water chambers may reach temperatures near room temperature. That matters because liquid water changes chemistry completely. In water, organic molecules can move faster, collide more often, and form more complex bonds. Titan's surface may be rich in organics, but the cold keeps much of that chemistry slow. Underground, warmth changes the rules. The deeper mystery is connection. Scientists suspect fractures in Titan's crust may allow some surface organics to slowly sink downward over geological time. At the same time, minerals from Titan's rocky core may dissolve upward into the water pockets. That creates a meeting place. Organic carbon from above, mineral nutrients from below, liquid water in the middle. A temporary laboratory for prebiotic chemistry. Each warm pocket may last thousands or millions of years before freezing again. Then new pockets form elsewhere. Titan's interior may be a cycle of birth and freezing, chemistry and silence, over and over again. Not a stable ocean, but a living geological process. If life needs repeated experiments, Titan may be running them constantly, quietly, deep below the surface, and if anything biological ever emerged there, it would be completely hidden from the world above. No sunlight, no sky, just warmth in darkness. But if Titan's hidden water matters for chemistry, then its surface chemistry matters just as much. Because Titan may be one of the few places where two different chemical worlds can meet. Titan is unlike any known world because it may host two completely different chemical environments at the same time. On the surface, liquid methane shapes rivers, lakes, and weather. Below the surface, liquid water may exist inside warm pockets of slush. Two solvents, two chemical systems, one moon. On Earth, all known life depends on water. Water dissolves molecules, supports reactions, and helps build biological structures. Titan's subsurface may offer that familiar pathway. But on the surface, methane acts as a completely different solvent. Slower, colder, less reactive, but still capable of organizing chemistry in strange ways. This creates something extraordinary. A molecule born in Titan's upper atmosphere might fall to the surface as organic dust, dissolve into a methane lake, move through rivers, settle into sediment, and over millions of years sink through fractures into liquid water below. The same molecule would experience two completely different chemical worlds in one lifetime. First hydrocarbon chemistry, then water chemistry. That transition may be one of Titan's greatest scientific opportunities, because when organic molecules move from methane into water, their behavior changes dramatically. Bonds break differently, structures rearrange, new reactions become possible. Titan may be creating a natural bridge between two kinds of chemistry that almost never meet. No other world we know offers this. Europa has water, but little surface organic complexity. Enceladus has water and organics, but its surface chemistry is limited. Titan has both, separated by ice but potentially connected over time. That makes it unique. A layered world where atmospheric chemistry feeds surface chemistry, and surface chemistry may eventually feed subsurface chemistry. A chain of chemical evolution stretching from sky to core. This raises a profound possibility. Titan may not simply preserve chemistry from the early solar system. It may still be evolving it, right now, at this moment. Under orange skies and frozen ground, molecules may be moving, reacting, organizing, changing. Perhaps slowly, perhaps imperfectly, but continuously. Titan may be less like a frozen fossil and more like an unfinished experiment, a world still searching for what chemistry can become, and that makes Titan far more than a moon. It makes Titan a model for worlds everywhere. Because if chemistry can organize itself here, then the universe may be full of places doing the same, hidden beneath ice, beneath atmospheres, beneath oceans, waiting for someone to look closely enough. For most of modern science, the search for life followed a simple rule. Follow the water, find liquid water, and you may find biology. That rule shaped how we search the universe. Mars became a target because it once had rivers. Europa became important because it may have an ocean. Enceladus became extraordinary because it sprays ocean water into space. Titan complicates that rule. Because Titan says water may not be enough, and it may not even be the beginning. Titan has water, but hidden. Its visible chemistry happens in methane, in hydrocarbon rain, lakes, and seas. It forces a larger question. What if life does not always begin in water? What if the earlier stages of life, the chemical steps before biology, can happen in entirely different liquids? That idea expands the map of habitability across the universe. Suddenly, cold worlds matter more, moons matter more, planets far outside traditional habitable zones matter more. Titan tells us that chemistry does not stop where warmth ends. It adapts, it slows, it changes form. But it continues. and that changes the mathematics of life in the cosmos. There are billions of gas giants in the galaxy. Around them may orbit countless moons. Some may be larger than Titan, some may have thicker atmospheres, deeper oceans, stronger tidal heating. If Titan exists here, then Titan-like worlds may be everywhere. Worlds where organic chemistry rains from the sky, where internal heat creates hidden water, where time and pressure build complexity in silence. The search for life may not be about finding another Earth. It may be about recognizing that Earth is only one version of a much larger story. Titan is proof of that. A world where chemistry found another path. Not better, not easier, just different. And if chemistry can organize differently, then life itself may be more common than we ever imagined. But Titan also teaches something humbling. We have barely begun to understand our own solar system. While humanity searched distant stars for alien worlds, one of the strangest worlds was orbiting Saturn the entire time, hidden behind haze waiting for us to notice. Imagine standing on Titan. The sky above you glows dim orange, thick with haze, so dense you cannot see Saturn hanging overhead. The sun is only a pale, bright patch in the fog, weak and distant. The air presses heavier than Earth's atmosphere, but gravity feels light, almost dreamlike. Beneath your feet, the ground is frozen water, hard as rock, coated in dark organic dust that fell from the sky over millions of years. Somewhere nearby, a dry riverbed curves through the land, carved by methane rain that may not return for years. Far away, black seas stretch beyond the horizon, liquid methane moving in tides under the dim light. Wind drifts across organic dunes, moving particles made in the sky. And far below, beneath kilometers of ice, pockets of warm water may be rising and freezing in silence. This is Titan. A world layered with hidden processes, each one stranger than the last. Weather above, rivers below, chemistry everywhere, warmth buried in darkness. It is one of the most alien landscapes humanity has ever discovered, and yet it is close enough that we can reach it. That may be the most shocking truth of all. Titan is not an exoplanet 40 light-years away. It is here, in our own solar system, close enough for machines to land, fly, and one day perhaps sail its seas, and still it remains mostly unknown. Most of Titan's surface has never been seen in detail. Most of its chemistry remains untested. Its hidden water has never been touched. Its deepest mysteries remain locked under ice and haze. Dragonfly will change some of that. It will fly across the dunes, sample the chemistry, and search for the missing steps between simple molecules and life. But Dragonfly is only the beginning. Titan's story will outlive the scientists now preparing to study it. Future missions may dive into Kraken Mare, drill through ice, map the hidden slush below, search for the chemistry of life directly. Titan is a world for generations of explorers, a place that refuses to reveal everything at once, layer by layer, secret by secret, and perhaps that is the real lesson Titan offers. The universe hides its deepest truths not always in distant galaxies, but sometimes in familiar places we thought we already understood. Titan teaches patience, curiosity, humility. Behind its orange atmosphere is not emptiness, but complexity beyond expectation. A world of fuel rain, frozen rivers, chemical snow, and hidden warmth. A world still becoming itself. And perhaps, in that slow becoming, Titan is telling us something about life itself. That life may begin quietly, slowly, hidden beneath layers of time and chemistry, waiting for the right conditions to awaken. Titan is still sleeping beneath its atmosphere, but one day it may answer the oldest question of all. Are we alone? Long before spacecraft crossed the outer solar system, Titan existed only as a point of light, a tiny companion to Saturn, barely visible through early telescopes, carrying no detail, no texture, no evidence of the strange world it truly was. And yet even then, Titan pulled at human imagination, because hidden worlds always do. In the 17th century, when Christian Huygens discovered Titan, the idea of moons itself was still new. The universe was changing fast. Earth was no longer the centre. Planets had companions. The heavens were not perfect spheres fixed in place, but moving systems of bodies, orbiting each other in silence. Titan became part of that new reality. But unlike Jupiter's bright moons, Titan remained stubbornly vague. Through every generation of telescopes, Titan stayed blurred, as if wrapped in smoke. Astronomers could track its orbit, calculate its period, estimate its size, but never its surface. That mystery made Titan different. It became one of the few nearby worlds humanity knew existed but could not see. There is something powerful about that. To know a world is there but not know what it looks like. To know it circles Saturn every 16 days, hidden in plain sight. For centuries, Titan remained that kind of mystery. Silent, unreachable, unexplained. Then, in the 20th century, science gave Titan a new identity. Not just a moon, but an atmosphere. That changed how people imagined it. Suddenly Titan was not a frozen rock in space. It was a world with air, weather perhaps, clouds perhaps, maybe even oceans. Science fiction seized on Titan long before science could confirm anything. Writers imagined hydrocarbon seas, exotic chemistry, strange alien weather, and in an unusual way, many of those guesses turned out to be right. Titan became one of the rare places where imagination and reality grew strangely close. But the deeper truth is this: Titan reminds us that wonder often begins before understanding, before the radar maps, before the landings, before the chemistry. There was simply a hidden world, and the human instinct to ask what was there. That instinct is what carried us to Titan, and it is the same instinct that will carry us farther still. For all we know about Titan, its seas remain almost untouched. We have seen them from orbit, measured their depths in places, watched sunlight glint off their surfaces and tracked their shorelines through the seasons. But we have never entered them, never floated on them, never tasted their chemistry directly. And that may be where Titan's next great discoveries wait. Imagine a future mission descending through Titan's haze and landing directly on Kraken Mare. Not on solid ground, but on liquid methane. A floating probe drifting across black hydrocarbon waves, measuring temperature, chemistry, currents, and dissolved organics. For the first time, humanity would not just observe Titan's seas, it would sail them. Scientists have already imagined such missions. Some propose submarines capable of diving beneath the surface, using sonar to map the sea floor and sample deeper layers of liquid. What would they find? Heavy hydrocarbons settled in darkness, organic sediments collecting at the bottom, chemical gradients where surface and depth differ. Perhaps even structures no laboratory on Earth has predicted. Titan's seas are valuable because they concentrate chemistry. Molecules that fall from the atmosphere do not remain scattered forever. They gather in liquid. They dissolve, collide, and reorganize. Over millions of years, Titan's seas may have become reservoirs of extraordinary chemical complexity. If the surface is where atmospheric chemistry lands, then the seas are where it accumulates. And if waves, tides, and evaporation keep those molecules moving, then Titan's seas may be among the most active chemical environments in the solar system. More active in some ways than Mars, more chemically dynamic than many icy moons. The question is not whether Titan's seas are interesting. The question is how much they have changed in the billions of years since they formed. Have they grown richer in organics? Have their shorelines evolved? Have they preserved ancient chemistry from Titan's earliest atmosphere? Or are they changing right now, season by season, wave by wave, molecule by molecule? Future exploration may answer that. A floating laboratory on Kraken Mare, a submarine in Ligaia Mare, perhaps even a shore mission where land meets liquid and chemistry becomes concentrated at the boundary. That edge, where methane waves touch frozen organic ground, may be one of the most chemically fertile places on Titan. Because boundaries matter. On Earth, coastlines are where chemistry often becomes organized. Tides concentrate molecules. Wet and dry cycles drive reactions. Titan may have its own version of that process, written not in water, but in fuel. And somewhere along those coastlines, chemistry may be waiting for the next step. Time moves differently on Titan. A single year on Titan lasts nearly 30 Earth years because Saturn takes that long to orbit the Sun. That means each season stretches for more than 7 Earth years. Imagine a winter lasting longer than an entire childhood, or a summer unfolding so slowly that storms arrive only once in a decade. Titan's climate lives on those timescales, and because of that, its surface changes with a patience almost impossible for humans to feel. Cassini was the first mission to watch Titan long enough to witness seasonal change. Over 13 years it observed clouds forming near the poles, shifting toward the equator, then fading again as sunlight angles changed. Entire weather systems migrated with the seasons. Methane clouds gathered like storms over Earth, but on Titan they moved slower, deeper, and colder, for some storms covered regions the size of countries. When they passed, the land below darkened, evidence of fresh rainfall. Then over weeks or months the darkness faded as methane evaporated or soaked into the ground. It was weather unfolding in slow motion. Titan's seasons also control its lakes. During colder periods, methane condenses and collects more easily. During warmer periods, evaporation dominates. This means Titan's coastlines breathe over decades, growing and shrinking like lungs. Some smaller lakes have disappeared entirely between observations, only to return later. It is a living climate system, slow but alive. The long seasons affect the atmosphere too. Winds change direction. Haze layers shift in altitude. Temperature gradients reorganize. Titan's entire sky tilts and wobbles with the changing sunlight. Recent atmospheric models show Titan's upper atmosphere behaves almost like a giant gyroscope, rotating and tilting in ways that influence storms below. That dynamic complexity matters because it shapes how chemistry moves across the moon. What falls at the equator today may be blown toward the poles over years. What rains at the poles may dry and return to the sky over decades. Titan's chemistry is seasonal, migrating through time like weather itself. On Titan, time is not just passing. It is sculpting the moon, season by season, storm by storm, molecule by molecule. Titan is one of the coldest places in the solar system where weather exists, and yet it contains all the ingredients for fire, methane, ethane, organic-rich air, fuel everywhere. It sounds like a contradiction, a frozen world full of fuel that cannot burn. But fire is not just about fuel, it needs oxygen, and Titan has almost none. That absence changes everything. If you could stand on Titan with a flame, nothing around you would ignite. The lakes would remain dark and still. The rivers would flow untouched. The methane in the air would not burn because the atmosphere lacks the oxygen needed for combustion. Titan is a world of fuel without flame, but that does not mean energy is absent. Titan burns chemically in another way. Sunlight acts as the spark, breaking methane apart high in the atmosphere and driving endless reactions. Instead of fire, Titan has photochemistry. Slow combustion written in ultraviolet light. The energy that on Earth creates weather through heat, on Titan creates chemistry through light. That difference makes Titan feel almost like an inverted Earth. Here, Here sunlight powers warmth and water cycles. There, sunlight powers chemistry and methane cycles. Even lightning on Titan remains uncertain. On Earth, lightning helps drive complex chemistry and storms. Some scientists once expected Titan's methane clouds might produce electrical discharges, but evidence remains weak. Its thick atmosphere may suppress strong lightning formation. If true, Titan's chemistry depends almost entirely on sunlight and internal heat, not sudden bursts of electrical energy. That changes how complexity grows. Slower, more patient, more stable. Titan's chemistry is not explosive. It accumulates, builds layer by layer, reaction by reaction. That patience may matter, because life or pre-life chemistry may not need violence. It may need time. Titan has time. Billions of years of it. Billions of years of fuel-rich chemistry unfolding without interruption. No flames, no burning, just molecules rearranging themselves in cold silence. In some ways, Titan is the opposite of fire. It is chemistry slowed to near stillness, but still moving. And sometimes, slow chemistry can go farther than fast chemistry ever could. Because what Titan lacks in heat, it makes up for in persistence. And persistence may be the most powerful force in the universe. What would Titan sound like? It is a strange question, but an important one. Sound depends on atmosphere, and Titan has one of the thickest atmospheres of any solid world in the solar system. In fact, its air is denser than Earth's. That means sound would travel differently there. Slower in some ways, richer in others, carried farther through the heavy nitrogen and methane air. If you stood on Titan's surface, the world would not be silent. Wind would move through dunes of organic sand, whispering across ridges shaped over millions of years. Methane rain would strike frozen ground with a soft, heavy rhythm, thicker and slower than rain on Earth. Rivers of liquid methane would flow through carved channels, producing currents and movement, though quieter than water, because methane behaves differently under extreme cold. Along the shores of Kraken Mare, waves would rise and fall against frozen coastlines, their sound softened by dense air and low gravity. Every movement would feel muted, slowed, almost dreamlike. Even your own voice would change. Titan's atmosphere would distort sound, carrying lower frequencies farther and altering the way speech moves through the air. A conversation on Titan would sound deeper, heavier, stretched. The world itself would seem to absorb sharpness. Scientists study sound because it reveals atmosphere. Future missions like Dragonfly may carry microphones, allowing humanity to hear Titan directly for the first time. Not through imagination, through data. The sound of wind, the sound of landing gear touching frozen organic ground, the sound of another world breathing. That matters because sound makes a world real. We have seen Titan through radar, we have sampled its atmosphere, but hearing it would create a new connection, a sensory bridge between Earth and Titan. And perhaps the strangest sound of all would be the silence between storms. Because Titan's weather is slow, its rain may come only once in years in some regions. In those long quiet periods, Titan may be one of the stillest places in the solar system. A world holding its breath beneath orange skies, waiting for the next storm, waiting for chemistry to continue its slow work. If you stood on Titan and looked up, you would expect to see Saturn dominating the sky. Titan orbits so close to Saturn that from space the gas giant appears enormous. But from Titan's surface, Saturn would often be invisible, hidden by the atmosphere. That is one of Titan's strangest illusions. The planet it belongs to disappears behind the same haze that hid Titan from us. The atmosphere is thick with suspended organic particles scattering sunlight in every direction. The sky glows orange, but not brightly. More like endless twilight. Shadows would be weak, blurred by scattered light. The sun itself would not appear as a sharp disk, only as a brighter patch behind the haze. Even at midday, Titan would feel dim, not dark like night, but muted, like late evening on Earth under heavy fog. Saturn would sometimes appear faintly overhead if atmospheric conditions allowed, a pale shape behind orange clouds, its rings barely visible, but often it would vanish completely. Imagine living beneath a sky where your giant parent planet is hidden most of the time. Titan's sky changes how distance feels. The atmosphere compresses the universe. Stars disappear. Saturn fades. Sunlight weakens. The sky becomes local, intimate, closed. It makes Titan feel less like a moon in open space, and more like a world sealed inside itself. That isolation may have shaped its chemistry. With little sunlight reaching the ground, surface reactions are slow. Most of Titan's active chemistry happens high in the atmosphere, where ultraviolet radiation still breaks methane apart. The surface receives the products of that chemistry like snowfall. This separation creates layers of activity. The sky builds molecules, the ground stores them, the seas dissolve them. The subsurface may transform them again. Titan is layered chemistry from top to bottom, and its sky is the first layer of that machine, a sky that hides Saturn, hides the stars, hides the sun, a sky that turns the universe into orange silence, and beneath that silence, an entire world continues changing, unseen except by the machines we have sent to touch it. Titan's gravity is gentle, only about 14% of Earth's. If you stood there, your body would feel almost weightless, light enough that every step would carry you farther than expected. A small jump on Earth would become a floating leap on Titan. Running would feel effortless, or almost like moving through a dream. But Titan's low gravity does more than change movement. It changes the world itself. Rivers flow differently. Rain falls differently. Waves rise differently. Methane rivers can carry material in ways water cannot on Earth, because the pull downward is weaker. Raindrops fall slower through the dense air, staying suspended longer, growing larger before impact. Dunes form under gentler wind forces. Even coastlines erode at different speeds. Gravity is one of the hidden architects of Titan's landscape. It shapes every process. But low gravity also helped preserve Titan's atmosphere. At first, that sounds impossible. Small worlds usually lose their gases, yet Titan kept its thick nitrogen blanket because its extreme cold slowed molecular escape. The balance between weak gravity and low temperature created a stable atmospheric prison. Without that balance, Titan would be airless. Without air, there would be no weather, no methane rain, no rivers, no seas. Titan's entire visible identity depends on that delicate relationship. Gravity also affects flight. This is why Dragonfly can exist at all. Titan's thick atmosphere and weak gravity make it one of the easiest places in the solar system to fly. Rotorcraft there require far less energy than on Earth. What would be difficult here becomes efficient there. In a strange way, Titan invites flight. It opens the sky. That matters because flight changes exploration. Instead of crawling across the surface like Mars rovers, Dragonfly will leap from dune to crater to plain, crossing in minutes what would take months on wheels. Titan's gravity, so weak and subtle, will become one of humanity's greatest advantages, a hidden gift from a moon that hides so much else. But gravity on Titan is not just about the surface. Deep inside, Saturn's gravity stretches Titan constantly, kneading its interior, creating friction, and perhaps generating the warmth that keeps water pockets alive far below. Even in Titan's depths, gravity never stops working. Titan is often imagined as flat. Seas, plains, dunes, endless lowlands beneath the orange haze. But Titan has mountains. Real mountain chains rising from the frozen crust, some reaching over 3,000 meters high, They were invisible for centuries, hidden by the atmosphere, until Cassini's radar began mapping the surface. At first, the mountain regions appeared as bright, rough zones in radar images, distinct from the dark, smooth seas and plains. Later analysis confirmed their heightened structure. These mountains are made primarily of water ice, but under Titan's temperatures, ice behaves like rock, hard, rigid, capable of holding massive structures over geological time. Titan's mountains reveal tectonic stress. The crust is not perfectly still. Internal forces push and pull, lifting ridges and folding the surface. Some ranges may be linked to cryovolcanism, where subsurface material rises upward through fractures. Others may be the result of crustal compression caused by internal cooling or tidal stress from Saturn. Titan is not geologically dead. Its mountains prove that. Imagine standing at the base of one of Titan's ice mountains. Above you rises a wall of frozen water harder than granite, coated with dark organic dust falling from the atmosphere. The sky glows orange. Wind moves across the ridges. Far below, river valleys carved by methane rain cut through the terrain. It would feel familiar and alien at the same time. Mountains matter because they change weather. They redirect winds, influence rainfall, shape drainage systems. Titan's rivers often begin in elevated terrain, just as rivers on Earth begin in mountains. The landscape is connected. High ground feeds valleys. Valleys feed lakes. Lakes feed atmosphere. Titan's climate and geology are tied together. Some mountain regions may also preserve older crust, areas less altered by erosion or chemical deposits. If Dragonfly or future missions reach these zones, they may find ancient layers of Titan's history exposed at the surface. Mountains are memory. Can they hold the deep past in stone, or in Titan's case, ice? And if Titan's mountains are shaped by internal movement, then that means the hidden world below is still pushing upward, still shaping the moon from the inside out. Titan's surface may look quiet, but the mountains suggest otherwise. Beneath the haze, beneath the rivers and dunes, Titan may still be moving, slowly, deeply, relentlessly. On Earth, volcanoes erupt fire. On Titan, if volcanoes exist, they erupt ice. Not solid ice, but slushy mixtures of water, ammonia, and methane rising from deep below the crust. Scientists call this cryovolcanism, and Titan may be one of the best places in the solar system where it happens. Cassini's radar revealed strange features that do not fit normal impact craters or mountain ranges. Broad domes, deep pits, or flow-like structures spreading outward across the surface. One of the strongest candidates is a region called Sotra Patera, where a deep depression sits beside elevated ridges and apparent flow fields. It looks, in many ways, like a volcanic complex, but instead of molten rock, the eruptions may involve cold liquid mixtures pushed upward by internal pressure. Why does this matter? Because cryovolcanoes may be Titan's methane source. The atmosphere constantly loses methane as sunlight breaks it apart. Yet methane remains. Something must replace it. Cryovolcanic eruptions could bring trapped methane from the interior to the surface, releasing it into the atmosphere over time. In that way, Titan's sky may be fed by hidden eruptions below. Cryovolcanoes also connect Titan's chemistry. Material from the interior reaches the surface. Surface organics can be buried and altered by fresh ice and liquid. This creates mixing zones where deep chemistry and atmospheric chemistry meet. Imagine a cryovolcano on Titan. Not glowing lava, but pale slush erupting into orange air, freezing quickly into strange ridges and plains. Methane gas escapes upward. Water-ammonia mixtures spread across the frozen ground. Chemistry begins again. If cryovolcanism is active today, Titan is even more dynamic than we think. It would mean the moon is still breathing from the inside, still reshaping itself, still feeding the atmosphere that hides it, and every eruption would be another chance for buried chemistry to return to the surface. Dragonfly will not land once, it will land many times. That is what makes it revolutionary. Unlike traditional landers that stay fixed in one place, Dragonfly will move, flying from site to site across Titan's surface like a robotic explorer carried by alien air. Its journey begins at Selk Crater, one of the most scientifically important places on Titan. Selk is an ancient impact crater around 80 kilometers across, where scientists believe liquid water once existed after the impact melted the icy crust. That temporary warmth may have allowed surface organics to react in water, preserving complex chemistry in the sediments left behind. Dragonfly will search those sediments. It'll drill into the ground, analyze samples, and look for large organic molecules that may have formed there. But Selk is only the beginning. Dragonfly will also fly across dune fields, sampling Titan's organic sands directly. It will compare chemistry between dunes and crater deposits, searching for patterns of increasing complexity. Each flight may cover kilometers at a time, carrying instruments across landscapes no human machine has ever touched. It will measure weather at every stop: wind speed, temperature, pressure, humidity. Titan's climate will be studied from inside the atmosphere, not just from orbit. Dragonfly will become part of Titan's weather while it explores. It may even encounter fresh storm deposits, areas recently touched by methane rain. That would offer a rare look at chemistry in motion, newly washed and reorganized by weather. Every landing site will be a new chapter in Titan's story. A crater where water once flowed, a dune where atmospheric organics gathered, a plain where methane rain altered the ground. Piece by piece, Dragonfly will connect Titan's systems together. Sky, land, weather, or chemistry. For the first time, Titan will be explored not as isolated discoveries, but as one connected world. And somewhere among those landing sites may be the answer to a question older than science itself. How close can chemistry come to life before it becomes alive? Titan may be holding that answer in its frozen ground, waiting for Dragonfly to wake it. Ice on Titan is not just frozen water, it is memory. Every layer of Titan's crust holds the record of billions of years of chemical fallout, rainfall, erosion, and internal movement. On Earth, ice traps bubbles of ancient air, preserving climate history like a time capsule. Titan's ice may do something similar, but on a planetary scale. Organic particles falling from the atmosphere settle onto the surface year after year, storm after storm, age after age. Some remain exposed. Some are buried by methane floods. Some are covered by fresh ice from possible cryovolcanic flows. Layer after layer builds up, storing chemical history like pages in a frozen archive. If Dragonfly or future missions can analyze those layers, they may reconstruct Titan's atmospheric past. How much methane existed billions of years ago? Was the atmosphere thicker? Were storms stronger? Were the seas larger? Titan's ice may hold those answers, but Titan's ice is not passive. Deep below the surface, pressure changes how ice behaves. It bends, flows, and slowly shifts under Titan's own weight. Different forms of ice may exist there, denser and stranger than the familiar ice on Earth. Entire underground layers may be moving over geological time, carrying trapped chemicals deeper into the moon. Then this movement may be part of Titan's hidden transport system, pushing surface organics toward the warm, slushy layers below. In that sense, Titan's crust is not just a shell, it is a conveyor belt, a slow machine moving chemistry inward. Imagine cutting through Titan's crust like slicing through a layered cake. At the top, organic dust from the sky. Below that, frozen river sediments. Deeper still, compressed ice rich with buried methane. Below that, slushy water pockets moving through frozen darkness. Every layer tells a different chapter of Titan's story, and together, they tell something larger. Titan has never been still. Even frozen worlds change. They store history in ways warm worlds erase. Titan's ice remembers what its atmosphere has forgotten. One day, Titan may become one of the most important destinations in human space exploration. Not because it is easy. Titan is far away, brutally cold, and wrapped in a thick atmosphere, but because it offers something rare: complexity. A world where atmosphere, weather, liquid, and chemistry all interact in ways we cannot fully reproduce on Earth. For future explorers, Titan presents unusual advantages. Its thick atmosphere protects against some radiation. Its low gravity makes landing easier than on many worlds. Flight's efficient. Machines can move far with little energy. In some ways, Titan may be easier to explore than Mars, but for humans, survival would still be almost impossible without advanced technology. The cold alone would freeze exposed materials instantly. Methane rain and hydrocarbon seas would make ordinary systems fail, and every tool would need redesigning for Titan's chemistry. Yet Titan offers resources. Methane itself is fuel. Water ice can provide oxygen and hydrogen if processed. Nitrogen fills the air. In theory, Titan contains many of the raw materials needed for long-term robotic or even human operations. It is a world rich in usable chemistry. Some scientists have imagined floating habitats drifting in Titan's atmosphere, where pressure and density would make buoyancy easier than on Earth. Others imagine submarine missions, deep drilling stations, airborne laboratories. Titan invites creative exploration because its environment is unlike anywhere else. More importantly, Titan offers perspective. It forces humanity to think beyond Earth-like worlds, to adapt not to familiar planets, but to radically different systems. Learning to explore Titan would mean learning to explore diversity itself. And that may matter for the future of space travel, because the universe is not full of Earths. It is full of strange worlds. Titan teaches us how to meet them, how to survive them, how to understand them. If Mars is practice for becoming interplanetary, Titan may be practice for becoming interstellar, a training ground for the truly alien. And if humanity ever reaches Titan in person, stepping onto frozen hydrocarbon sands beneath orange skies, it will not just be another landing. It will be a meeting between two kinds of worlds, the warm biological world that made us, and the cold chemical world that may reveal where life itself begins. If there is one question that shadows every mission to Titan, it is this: can a world like this teach us how life began? Not how life survives, not how life evolves after it already exists, but how lifeless chemistry crosses the invisible boundary into biology. Titan may be one of the few places in the solar system where that boundary is still preserved. On Earth, the earliest chapter of life is gone. Our planet is too active. Plate tectonics recycled the crust. Oceans churned. Volcanoes erased evidence. Billions of years of biology transformed the chemistry that came before it. Earth's origin story has been rewritten too many times, but Titan is different. Titan is cold enough to preserve ancient chemistry, almost like a freezer preserving food. Reactions happen, but slowly. Materials fall from the atmosphere and remain on the surface for immense spans of time. In some places, organics may have remained nearly unchanged for hundreds of millions of years. Again, that makes Titan a chemical museum of prebiotic possibility. High in Titan's atmosphere, sunlight breaks methane and nitrogen apart, forming larger carbon-rich molecules. These compounds drift downward like dust, collecting across the moon's surface. On early Earth, similar molecules may have existed before life appeared. Hydrogen cyanide, simple hydrocarbons, nitriles. These are not random compounds. In laboratory experiments on Earth, such molecules can form amino acid precursors, nucleotide precursors, and membrane-building compounds, the building blocks of life. Titan may be manufacturing those same building blocks right now, but the deeper question is whether Titan's chemistry can organize itself. Complexity alone is not enough. Life requires structure, separation, repetition, selection. Some of the most exciting recent experiments suggest Titan-like hydrocarbons can form membrane-like structures in liquid methane. Tiny chemical boundaries, primitive compartments that separate inside from outside. On Earth, cell membranes were a critical step toward life. On Titan, similar boundaries may form under completely different chemical rules. That possibility changes biology itself. It suggests the path toward life may not belong only to water. Titan may be showing us a second road, a slower road, a colder road, but still a road. And if Titan's buried water pockets occasionally mix with surface organics, then chemistry could become even more powerful. Molecules formed in methane may someday encounter water below, shifting into a completely different reaction environment. In that transition, new possibilities emerge. Titan may not just preserve the origin of life's ingredients, it may be actively experimenting with them, quietly, slowly, across billions of years. The greatest mystery may not be whether Titan has life. It may be whether Titan is still deciding. For all the maps, all the flybys, all the landings, Titan remains one of the least understood major worlds in our solar system. That is extraordinary when you think about it. We have walked on the moon, driven across Mars, flown through the plumes of Enceladus, landed on comets, even photographed Pluto in detail. And yet Titan, one of the largest moons in the solar system, remains deeply hidden. Its atmosphere still protects its secrets. Radar has mapped much of the surface, but not with the clarity of direct sight. Large regions remain poorly understood. Some areas have only been observed a handful of times. Entire landscapes may exist there that we have never imagined. Unknown coastlines, unmapped mountains, buried cryovolcanoes, hidden lakes. Titan remains unfinished science, and that makes it rare. In the modern age, mystery has become harder to find close to home. Most nearby worlds have been stripped of their unknowns, reduced to maps and measurements. Titan resists that. It still feels like an age of exploration world, a place where the next mission could discover something entirely unexpected. That is perhaps Titan's greatest power. It reminds us that discovery is not over. Even in our own cosmic neighborhood, entire worlds remain partly invisible. Titan is a reminder that the universe keeps its secrets carefully. Not always far away, but often just behind a layer of haze. Waiting for better tools, better questions, better patience. Dragonfly will reduce some of that mystery. It will sample the ground, study the chemistry, and map local regions in detail. But Titan is vast, larger than Mercury. Dragonfly will explore only a tiny fraction of it. The rest will remain for future generations, future orbiters, future sea probes, future drills, perhaps future humans. Titan is not the end of a story. It is the beginning of one, a world whose mysteries are layered, patient, and deep. And in many ways that makes Titan the last hidden world close to home. Not because it is the last place we can reach, but because it still has the power to surprise us. In a solar system increasingly familiar, Titan remains gloriously strange. A moon of fuel rain, buried water, organic deserts, and seas blacker than night. A world that refuses to be simple. A world still holding back answers, and perhaps the greatest answer of all may still lie beneath the ice, beneath the chemistry, beneath the haze, waiting for the moment when we finally ask the right question. Time on Titan flows differently, not because the laws of physics change, but because the processes that shape the moon operate on scales unfamiliar to humans. Methane rain may fall only once in a decade in certain regions. Rivers carve valleys over thousands of years. Organic particles descend from the atmosphere and accumulate layer by layer over millions. Ice slowly shifts and bends, carrying buried chemicals toward the warm pockets below. Titan's clock is measured not in hours or years, but in centuries and geological epochs. That slowness affects everything we observe, and storms appear rare but massive. Lakes fill and drain in patterns unseen in human lifetimes. Mountains form and erode almost imperceptibly. Even Dragonfly, flying across dunes and craters over 3 years, will witness only a fragment of Titan's slow choreography. Yet within that slowness is a kind of reliability. Chemistry builds steadily. Organics persist. Layer by layer, season by season, Titan creates a record of its own evolution. Each layer tells a story. Each storm leaves a trace. Each river valley marks a passage of time, and every pocket of water buried deep within the slushy ice carries the cumulative memory of the forces acting above and below. In that sense, Titan is a slow clock, measuring the eons in quiet chemical steps and geological movements. It is a world where patience is a force as powerful as wind or rain, and where discovery requires matching the moon's own rhythm. Understanding Titan means adjusting our sense of time. Minutes, years, and decades matter differently here. Processes unfold slowly, but their cumulative effect is enormous. Rivers carve landscapes, ice moves, chemistry evolves. In human terms, Titan seems almost frozen, yet in planetary terms it is alive. It is a clock running not in hours but in patience, steadily ticking toward chemical complexity, potentially toward the edge of life itself. And for those willing to watch, Titan teaches that the universe does not always hurry. Sometimes, the slowest worlds hold the deepest secrets. Every day on Titan, the sky manufactures organic molecules. Methane and nitrogen high in the atmosphere break apart under sunlight, recombine into heavier hydrocarbons and nitriles, and gradually descend toward the surface. They fall like snow, layer upon layer, covering the frozen plains with sticky reddish-brown particles called tholins. These particles are not uniform. Some are fine dust, some cluster into larger grains, some settle in dunes, others in riverbeds. Over millions of years, the surface becomes a layered archive of chemical reactions, preserving a record of Titan's atmospheric activity. The rainfall of organics is slow, patient, and relentless. Each grain is a molecule of potential, a fragment of prebiotic chemistry preserved in frozen time. Rivers, lakes, and seas transport these molecules further. Methane flows collect organics and move them across valleys. Evaporation leaves behind concentrated residues. Winds sculpt dunes of organics into ridges hundreds of meters high, arranging molecules in patterns created purely by planetary forces. The process is natural but resembles a laboratory experiment running on a planetary scale. Titan's surface is not static, it is dynamic, continuously interacting with the chemistry raining from the sky. Each storm, each river, each dune reshaping spreads molecules into new arrangements. That layering creates opportunities. Molecules meet others they might never encounter in isolation. Gradients form, concentrations arise. Energy from sunlight or tidal friction interacts with these molecules. Over geological time, that combination of preservation, mixing, and energy creates a natural environment where chemistry can evolve steadily. Titan's snow of organics may be one of the most powerful tools in understanding prebiotic processes in the solar system. It is everywhere, being persistent, patient, and waiting. And as we study Titan more closely, these frozen chemical archives may reveal how far simple molecules can go when time is on their side. The surface may not yet harbour life, but it preserves the conditions that could allow life to emerge elsewhere, or perhaps below, where warmth meets the organic legacy from above. Titan's snow is silent, slow, and profound. It is the universe writing its chemistry one particle at a time. Beneath Titan's orange haze, rivers flow silently, invisible until a spacecraft or radar reveals them. These rivers are not water, not like anything on Earth, but liquid methane carving valleys into water ice harder than granite. They follow familiar patterns, tributaries merging into larger channels, meanders cutting across plains, floodplains forming where liquid collects. Nay, yet every aspect is alien. Flow is slower, viscosity lower, gravity weaker. The liquid behaves differently, but the landscape it shapes is surprisingly recognizable. Huygens revealed a riverbed littered with rounded ice pebbles, evidence of transport by flowing methane, smooth edges, shapes shaped over countless cycles of erosion. Even in the absence of frequent rain, these channels preserve the memory of storms from decades or centuries ago. Some rivers feed into lakes and seas, some dry into depressions, leaving behind layers of organics that continue Titan's slow chemical cycle. This network is part of a larger system. Atmospheric photochemistry creates organics that fall to the surface. Methane rain collects them into channels. Rivers carry them to lakes or seas, where they dissolve and settle. Winds redistribute particles into dunes, completing a planet-scale chemical loop. Titan's rivers, though alien in composition, operate as conveyors of material and energy, connecting sky, surface, and subsurface. They are not just channels of liquid, they are highways of chemistry, moving molecules across the moon in patterns shaped by time, gravity, and weather. For scientists, mapping these rivers is essential. Each bend, each delta, each dry riverbed tells a story about climate cycles, chemical distribution, and the interaction between Titan's interior and surface. Titan's rivers are slow, patient, and continuous, a reminder that alien worlds may function differently, yet in ways that echo Earth. They teach that water is not the only liquid capable of shaping landscapes and redistributing chemistry. Methane can do the same, quietly, over eons. The hidden rivers of Titan are living maps, waiting for explorers to trace their paths and uncover the chemical history carried within each drop. Beneath the rivers, dunes, and seas, Titan holds yet another layer of mystery. Its crust, hundreds of kilometers thick, is not solid rock, but water ice behaving like stone. Beneath that, a slushy layer of ice and liquid water may exist, forming a network of isolated pockets where warmth from tidal friction melts ice and maintains liquid at surprising temperatures. These pockets may reach near room temperature in isolated regions, enough to sustain active chemistry. Minerals from Titan's rocky core can dissolve into these waters, while surface organics percolate downward through fractures, creating transient chemical laboratories. Each pocket is isolated, unique in temperature, composition, and pressure. Unlike a global ocean, these pockets are distributed, heterogeneous, and constantly changing. Some may freeze over millennia, new ones form beneath them. This dynamic structure transforms our understanding of Titan. It is not simply a moon with methane lakes above water ice below. It is a world with multiple chemical environments interacting slowly over vast spans of time. Each layer, atmosphere, surface, slush, water pockets, connects through gradients of energy, material, and chemical reactions. Titan's internal dynamics, fed by Saturn's tidal forces, are as important as its surface. The slushy layer is not inert. It moves, shifts, and transfers materials upward and downward, linking distant regions and potentially concentrating organics in ways we have yet to understand. In essence, Titan is a nested laboratory, a world where chemistry evolves under cold, slow, and patient conditions, allowing processes that might not survive elsewhere. Dragonfly will probe only the top layers, but even that limited access may provide clues about deeper interactions, the slow movement of materials, and the potential for prebiotic chemistry below. Titan's secrets are layered, patient, and alien, still waiting for discovery. Titan is more than a moon. It is a teacher. Its rivers, seas, dunes, and haze reveal a world that operates on principles familiar yet alien. Chemistry runs slowly, patiently, across layers that span atmosphere, surface, and interior. Weather moves at the pace of decades, storms shaping the land over centuries. Methane flows carve valleys through frozen water ice. Organic particles fall like snow, accumulating in dunes and plains, and forming a chemical record that preserves billions of years of planetary history. Deep below, warm pockets of water rise through slush, carrying minerals and organics in a hidden cycle. Titan shows that life, or the chemical potential for life, does not require Earth-like conditions. It may thrive where warmth is rare, where liquids differ from water, where gravity is weak, and seasons last decades. Titan challenges the traditional search for habitability. Life may not be confined to the habitable zone of stars. It may exist wherever chemistry, energy, and time align, even on worlds far colder, slower, and more distant than Earth. For humanity, Titan is a laboratory for imagination. It teaches that persistence matters, that patient chemical evolution can occur over eons in places we might dismiss as frozen or barren. Titan's complexity, hidden for centuries, reminds us that the universe is full of surprises close to home. It is proof that the most extraordinary discoveries do not always lie in distant galaxies, but sometimes in places we think we already understand. Titan invites us to ask deeper questions, to look beneath layers, to imagine not just what life is, but how it begins. It's a world where every storm, every river, every pocket of water carries a lesson about chemistry, time, and the possibilities that emerge when a planet or a moon operates on its own rhythm. The story of Titan is far from finished. Huygens gave us the first touch of its surface. Cassini mapped its rivers, lakes, and mountains. Dragonfly will explore its dunes, craters, and chemical landscapes, connecting the atmosphere, surface, and shallow subsurface. Yet Titan is vast. Most of its secrets remain beyond our reach. The hydrocarbon seas, the deep slush layers, the hidden pockets of warm water, the ancient chemistry preserved in ice, all await future explorers. Titan challenges humanity not just to observe, but to adapt, to design machines that can fly in dense, cold air, survive methane rain, navigate dunes, and sample chemistry without contamination. It asks us to think beyond Earth-like paradigms, to consider new forms of chemistry, new timescales, and new possibilities for life. The discoveries on Titan will not come quickly. They will unfold over decades, perhaps centuries. Each mission will peel back a layer of the orange haze, revealing new landscapes, new chemical interactions, new surprises. Titan is a relay of exploration, a challenge for generations of scientists and engineers. It is a world that teaches patience, curiosity, and humility. For anyone who stands beneath its orange sky in imagination or in data, Titan is a reminder that the universe is stranger than we expect. That complexity can hide behind seemingly simple surfaces. That life's ingredients may emerge in unexpected ways. And that even within our solar system, one of the most alien, chemically rich and layered worlds has been waiting all along, patient and silent, ready to teach us what it means to explore, to observe, and to wonder. Titan is not just a moon. It is a nested world of secrets, and it is only beginning to reveal itself.